Now we introduce the multi-rail flow path. The flow path of an oscillation doesn't have to be a single rail as it is up here. It just has to look like a single rail to the closure path. So we have to define the flow path in such a way that it monotonically transitions between two states that can be logically detected and reduced to the monotonic oscillation of the closure path. Now we do this by defining completeness relations on the flow path. And we begin by defining red to mean data and blue to mean not data, or null. We'll call blue null. And we define a data transition completeness to be the transition of one rail to data. The other two rails remain null. It can be any one rail, but it's only one rail transitions to data. The other two remain null. And we define null completeness to be all rails null. So when that one rail transition to data transitions back to null, all the rails are null, and that's our null completeness. So we have these two completeness conditions defined on the flow path. Now, the NCL threshold functions are defined in terms of completeness conditions also. And that's what the threshold is. For a 3 of 5 gate, for instance, when 3 inputs become data, that's completeness for the gate, and it will transition its output to data. Now, for all the gates, all the inputs have to become null before the gate transitions its output to be null. So each NCL threshold gate has a definition of data completeness and a definition of null completeness. So here we have a threshold 1 function, a threshold 1 gate, with 3 inputs. So when one input becomes data, it will transition its output to data. And when all 3 inputs become null, it will transition its output to null. So this gate is appreciating, it's detecting the completeness relations on the flow path, right? So this gate will determine when data completeness occurs, and it will determine when null completeness occurs. And its output will drive the closure path directly, right? So this gate is detecting the completeness behaviors on the flow path and reducing them to the monotonic completeness behavior of the closure path. So now you'll notice the closure path goes backwards. It's inverted, and it's presented to a rank of gates across the flow path. Now this rank of gates is an enable rank. Now this is 2 of 2 gates, so this threshold 2, only when both inputs are data will it transition its output to data, and only when both inputs are null will it transition its output to null. So when the closure path is data, that means, and the data wavefront comes along, 2 inputs of a gate will be data, and it will transition its output to data. So the way the data wavefront is propagated through the enable rank, and also the enable rank will maintain that data wavefront. As long as the closure path remains data, this rank will maintain that data value as it propagates through the oscillation. Now, as the wavefront propagates, it will propagate through another enable rank here, which is the enable rank for the downstream oscillation. So when this downstream oscillation, the closure becomes data, it allows the data through, it's going to maintain the data, and we detect strictly after that our own data propagation. So this gate detecting data completeness means that the downstream oscillation has accepted the data wavefront and is stably maintaining it, and we can change our input. So this becomes data, this transitions, inverts to null, and now this is presenting null to the enable rank, and a null wavefront can play through. And the null wavefront, as long as the closure remains null, the null wavefront will be maintained as it propagates through the oscillation and through this rank, and as soon as it propagates through here, the downstream oscillation has accepted it. This detects null, this becomes null, this is inverted to data, and will allow a data wavefront through. Now, this rank of enable gates and the following completeness detection is the completeness behavior that links the oscillations now. Up here, the completeness behavior was a single gate that linked the oscillations. Now the completeness behavior is the enable rank and the following completeness detection. And you'll notice that this structure of oscillations is oscillating in exactly the same way that this structure of oscillations is oscillating. Their oscillation behavior is identical. The only difference now is that this structure of oscillations is propagating real data through its flow path. So we're propagating successive packets of discrete data through the flow path from oscillation to oscillation through the structure of oscillations. Now, this flow path will become more complex as we go along, and the structure of oscillations will become more complex as we go along. But it all derives from this foundation: linked oscillations propagating real data along a flow path through the structure of oscillations. Okay, let's look at a few examples. We're going to rapidly run out of steam specifying circuits with graphical pictures, so we're going to start introducing a symbolic specification. The first specification is the token, which specifies the structure of the flow path. And this specifies a flow path of 4 rails named 0, 1, 2, and 3, and the flow path itself is named A. And the rails of the flow path are OR related. The curly braces mean they're OR related, and that means that only one rail per oscillation will transition to data. The next specification is the flow component, and this specifies the linkage of oscillations. Okay, so with the flow components, we specify the structure of oscillation linkages. So this specifies that A flows to B, and it's linked with B. And later on, there'll be more structure to the flow component. The flow will be somewhat more detail in the flow. The body will have logic that occurs during the flow, and the closure will indicate how the flow is, how the oscillation is closed. And in this case, A flows to B. No changes occurred, and so A flows to B. The body indicates that A flows to B, and the completeness of B closes A. So B/# means refers to the completeness of B. So now, if none of this is included, we just say A flows to B, then all of this is implied. It implies that A flows to B without any change, and that the completeness of B closes A. And we have another couple of things. The source, something flows to B from somewhere, and a sink, A flows to nowhere. So this is our first circuit, the pipeline. This is the symbolic specification, and these are the graphic specifications. So A is presented, and it's presented with a auto-produce module. So the A comes from someplace means it's an auto-produce. It's a source of some kind, and we'll see different kinds of sources later. So this source, A flows to B, B flows to C, C to D, D to E, and then E is auto-consumed, right? And this is an auto-consume module. So now we will define these in terms of components, and a component links 2 or more oscillations, right? So this is a component linking 2 oscillations, and this is the linkage structure. The completeness of B is the closure path back to the source. The completeness of C closes with A, and so forth. And so the components are bounded by rails, by signal paths, by flow paths, rails of flow paths. So we connect components simply by connecting the rails. Okay, so this is the pipeline connected together down here, and this, shows the same symbolic specification. But these are the individual components, and then this is them connected. So this is the specification of the pipeline. It's 4 flow paths of 4 rails, each named 0, 1, 2, and 3, and all of these flow path names are OR related. So only one rail at a time becomes data. And so this is our symbolic specification. This is the Verilog specification. And this is a component down here. And this is a module, the Verilog module, that specifies the component. So this is the 4 rails. A flows to Z, A0 flows to Z, A1 flows to Z1, A2 flows to Z2, A3 flows to Z3. So it's just straight through. This is the completeness. This is the completeness of Z creating a comp that is going to close with A, and this is the completeness from downstream Z comp that is going to enable the flow of Z. So this is the component, and this is just connects the 4 components together. Right? A flows to B, B then flows to C, C flows to D, D flows to E, and then E is auto-consumed. We produce E comp, which is going to close with E, and A is auto-produced, and in this program only A0 is auto-produced, and A1, 2, and 3 are constants. So this pipeline is just going to pipe A equals 0 continually, auto-produce A equals 0 continually, and pipe it through the pipeline. Now our next example is the ring. This is the name of the Verilog program. I should have said this is also the name of the Verilog program. And this is the specification. Now on the ring, we have some change in along the flow path, right? So the rails are mixed up here. So A3 flows to B2, A flows through to B1, and A0 to B3. And so this is the flow of A to B. So now we have a body to specify. And we specify that A3 flows to B2, A2 flows to B1, A1 flows to B0, and A0 flows to B3. Now this is the flow of A to B, and the completeness of B closes with A, right? So this is a full specification of a component with a body and so forth. So now we have to initialize a data wavefront in the ring. And this stage initializes the data wavefront. So we initialize A0, and the other rails have to be initialized to null. And also the next component has to initialize the rail to null that's going to block the data initialized here, so that we have null flowing around the ring to initialize the ring. Right, so these are all null and they'll flow around, but this is initialized to data, then this is initialized to null, and the null will flow around. So now we have a few different components. This is a component that initializes to N. That's going to be this one. It initializes one rail to N, and this is the one that changes the rails. A1 goes to Z0, A2 goes to Z1, and so forth. So this is the component that initializes the data rail and the 3 null rails. So that's going to be this component. And then this is the general component that we saw before. And then this connects the components together. And we have component N, component D, and the 2 general components. And A flows to B, B flows to D. And now you notice that D flows to A, right? It goes back to A. So that makes the ring. So now we put the ring and the pipeline together, and the ring becomes a source for the pipeline. And the ring is just like before. The rails are changing each time the data wavefront flows around the pipeline. So now the ring source is presenting varying data to the pipeline, which will flow through the pipeline. So now we've given the module ring4gen a name that can be referenced. The same up here in the symbolic specification. We've given the component specification a name, and it can be referenced, and it just has an output. It doesn't have any input. And over here we reference ring4gen, and that's how we get A for our pipeline, and then A flows to B and so forth through the pipeline. So now with the ring is the same as the ring before, except that we're pulling out C and sending it to the pipeline as well as sending it to D. So now C goes to 2 places, right? And up here you can see C goes to D and out. And down here C flows to D, and we also assign C to out in the module interface. So now that C is going to two places, it has to be closed from two places, right? So we have to close C from the pipeline and from the completeness of D. So C is closed, you'll notice, with the completeness of D and the completeness of out. So the brackets here mean they're in an and relationship. We'll get into this much later about the and/or relationships in the specification. But this means that the completeness of D and the completeness of out close C. And down here we have out comp comes in, out goes out, and out comp comes in. So here we combine out comp and C comp with a 2 of 2 and CC2 comp, which is going to enable C. Right, so this is the 2 of 2 combining the two closures into the single enable of the C flow. So down here we've named this, and we also, and the pipeline is the same as before, except now that we're referring to ring 4 gen to get the flow of A, and we're closing with A comp, which comes out of the pipe component. So now we have a flow path. We're altering the data in the flow path, and we're flowing real information through the flow path. You can think of this flow path as a 4-value variable, and one value at a time, one rail at a time becomes data, and each data wavefront is flowing an individual value and flowing information through the flow path.